Our first keynote speaker is going to be Dr. Philip Bonnaventure from the Department of Geography here at Queen's University. Dr. Bonnaventure did his undergrad and master's at the University of Ottawa in physical geography. Working under the supervision of Dr. Antony Luguich, Dr. Bonnaventure completed his PhD, specializing in geocryology and climate change in 2011. Yeah, remember when I said we're going to try to make things simple? I took this off the website. It's not simple. He then came to Queen's University to work as a postdoctorate research fellow in the Department of Geography here. At the broadest scale of Dr. Bonaventure's research interest, he focuses on the use of geomatic modeling in environmental systems at different scales of time and space. Specifically, he's interested in using these types of data collected in high Arctic and in mountain ecosystems to understand the evolution of terrestrial and fluvial landscapes in the past, present, and hopefully in the future. We'll find out. His current research focuses on two distinctive projects, which examine terrain in the Yukon and Melville Island in Nunavut. These projects investigate and model current, past, and future spatial distributions of permafrost, as well as examining the link between permafrost thaw and budgets of water, sediment, salt, and carbon through the distribution mechanism of hydrological processes. His aim is to expand the scales of the research both temporally and spatially in order to include the modeling and evolution of northern landscapes. Without further ado, please let me hand off to Dr. Philip Bonnaventure, who will be presenting this talk titled A Scenario-Based Approach to Future Climate, Modeling from the Viewpoint of Human Behavior.
All right, so let's get this talk up here. There we go. I've never operated with a podium that I can move up and down before, so let's watch that again. All right. At least that was a hit, so there we go. All right, well, thank you very much, Daz, for the introduction. When Daz asked me to do this, I had no idea what to expect. I thought it was going to be a couple of the people from the department in a room, and that was going to be it. And I'm very pleasantly surprised to see that that is not the case, as was said before me. So getting along with this talk, really, what the other thing is, the advantage of going first is not only do you not know what to expect, but at least it allows you to basically say whatever it is that you want without worrying about somebody else having covered your topic and you not being at the lecture to actually see what's going on. That being said, most of the time what I look like is something along this picture. I don't look like I do today, as pronounced or as nicely put together as I normally do. Most of the time I'm on some godforsaken island somewhere, starving to death, trying not to be very cold and wet, such as in this picture. One of the things is, as well, is I'm very glad to see that there is nobody with a sign saying climate change is a sham or anything along the lines of that, which I was half expecting as well. So, while some of my colleagues also led me to believe that they would be providing those signs, and there is no evidence of that to this point. So one of the things that comes up whenever somebody identifies themselves as working within the realm of climate change is you have to ask the question is, how do I study climate change? And Daz kind of alluded to this, that my project really takes an understanding at looking not necessarily at the mechanisms or the driving forces behind climate change, but really looking at how the environment, how the processes in the environment are really steered by climatic change. So what I focus on is in particular, permafrost environments and northern or cold-based environments and how things are changing in both the terrestrial systems and the aquatic systems as well. So really I focus on the idea of how does climate change drive these processes. That being said as well, because there was not necessarily that much put into what I had to speak about, I'm able to speak about, for the most part, what I want to be able to speak about. And I want to focus on the differences between weather and climate to start with. These are some of the ideas that I say to any climatology class that I teach or climate change class, that this is the first topic of the lecture that I will cover, and it will be the first question on your final exam as well. That being said, looking at these two distinctions is really going to be the focus of what we're doing and what I do in actually modeling climate, and more specifically, the reaction of these systems to climatic change compared to meteorological changes. So if we look at meteorology in general, what we can see is that this is the study of atmospheric processes, we can see that this is responsible for weather. And weather and climate are inherently related to one another. Climatology, on the other hand, is a very scientific word that basically looks at the study of climate. So one of the questions that you might be asking yourself is that what are the differences between these terms? And it's a very good question, and if you know the answer, please communicate it to anybody in my first year climatology class. Well, it's the second year class, I guess, because it'll be the first question on your exam. But the difference really looks at time, and it's the temporal component that we're looking at with respect to this. How long of a time, you might say? Is this thousands of years? Is it millions of years? Well, how we measure it is over a 30-year time period. This is how we can get and gauge how things are changing. With respect to climate, though, and of course meteorology as well, this really factors in. We have several factors that we can actually look at that are elements of climate. So what are the rules that actually make up what is going on with respect to climate? How do we actually speak about it? How do we describe what it is in these various areas? And of course, these are things that you probably think about on a daily basis. Elements of climate include things like temperature. Probably one of the most important with respect to what's going on with the weather. What is it? Well, temperature in reality is a measurement of average kinetic energy, but most people interpret it as, how hot or cold it is. These days, people are very interested in what the temperature is before you want to go outside. Equally as important to that is, of course, precipitation. What is it doing? Did it snow last night? Do I have to go out and clean my car this morning before I get off to work or wherever it is that I am going? Of course, precipitation is much more important than just, being a nuisance or anything along the lines of that. It's very important with respect to a lot of the things that are very important to human beings, such as farming. It helps this, as is temperature, as we've mentioned. Other things that become important include things like wind speed. So this not only affects things like temperature, it affects precipitation through things like evaporation as well, but it can be very important depending on the areas in which you live in. Wind direction also goes hand in hand with that one, as does things like relative humidity, the amount of moisture that's in the air. These are all things that make up and describe climate. If we look at other things that are important, this covers things like evaporation in terms such as that, as well as insolation, and that's how much solar radiation is actually coming down and radiating on the Earth, and that comes into the cloud cover. All things that you can see and that would change on kind of a daily basis, both elements of climate and elements of meteorology at the same time. Now, in particular, this being a talk on climate modeling, and we're trying to get an idea as to how this is really brought to the forefront, how we actually represent that. We bring in influences of climate, and these are things that actually vary those elements from place to place geographically on the Earth. We obviously know that the Earth is not the same with respect to the various different weather patterns that we have, also the various different climates that we have. So what are those elements that come into it? And those influences that actually are steering those elements? And they're things that are very logical in general. There are things like latitude, your position relative to the equator. The further you are from the equator, the less direct solar radiation you receive. As well as elevation. Elevation, how high up you are in the atmosphere while staying on the Earth's surface. This is also quite important when looking at these elements. Distribution of land at sea is another one. And looking at the different properties that exist with respect to water versus land. They heat up very differently. This is why water retains energy quite a bit more into the cooling season than does land. The nature of ocean currents as well. Might have always struck people as very interesting why somewhere like Kingston is quite a bit colder than somewhere like Paris, which is further north. And that has a lot to do with the nature of ocean currents. Distributions of mountain barriers. One of the things that I've spent a great deal of my studies looking at is the effect, the microclimatological effect of mountains and elevation on these particular temperature phenomena, and that's in there as well as the patterns of prevailing winds and the locations of main centers of high and low pressure. So these are kind of the rules, and when you ever look at anything, whatever it might be, with respect to these systems, it's important to understand the rules in which govern and which bring them together. And that introduces the idea of climatic change. And I'm quite fortunate to be the first one who gets to talk about climatic change because it means that I'm saying this in this lecture series for the first time. And it struck me as quite interesting is that when you teach classes, one of the interesting things, and some of my friends find this interesting, is that you pretty much can write the textbook companies and say, I would like a copy of your textbook, and very promptly it comes to your desk. And that being said, I received quite a few books on climatic change. They all say different perspectives. They all look at various different elements of climatic change, everything from the highly scientific to what it means to things like farming, what it means to water safety and supplies. And in one of those books, actually, what I can see is that I saw this quote, and this quote actually stuck with me quite a bit, the idea that climate change is now being billed as a major threat to humanity. And I thought to myself when I read that, all right, well, that's worth another read when it comes down to it. So it allowed me to comprise this slide. And I was thinking, why would this be a major threat to humanity? This was one of these things, thinking outside the box. When you have a population of 7 billion, well, that's pretty impressive, to be honest. It would take quite a bit to take that down. And the more and more I thought about this, the less and less I actually believed it. Because what you actually look at with respect to this is not necessarily thought of in the same way when you think about climatic change. If you think of some of the elements that we're looking at, the basic survival needs for human beings, well, we're talking about some pretty obvious ones. Oxygen is a prime example of that. You can't go very long without oxygen. Other things you can't go long without are water, of course. Just maybe a day, maybe two, probably not going to be very happy after that. Food as well, things like shelter, and of course things like clothing and sanitation. That's another big one. Well, if we look at those in the light of climate change, well, what we can see is that several of them are actually highly, highly threatened by changes in our climate that are actually ongoing. Oftentimes people think of climate as being, and climate change, as being something that's very, very abrupt, that we're going to see coming very apocalyptic in nature, when in reality it's a lot of seemingly slow changes when it comes to the perspective of things like human lives. This is really what we're looking at, and what I tend to focus on quite a bit is the temporal component to what is actually happening with respect to how climate change is evolving. So looking at that forced me to look at some of the definitions when it came to teaching this material for the first time. And climate change, as it's defined, is really put forth as being, a change in the significant statistical distribution of weather patterns ranging from times from decades to millions of years. And of course, that's a very, very broad definition of climate change. It actually has two definitions of two different types of climate change in there. Now, this might be a change in the average weather patterns that we're looking at, or the average climate of an area, or it could be synonymous with looking at major events, major differences that we're actually seeing in these events, extreme events for the most part. We'll comment on those as well. But for the most part, climate change can be seen as an umbrella term. And under that umbrella is basically several different things. And when we study climate change, as I mentioned, people look at both the mechanisms of climate change as well as what happens as a result of climate change. There are several things that we need to consider. And the first, of course, global warming. Ideas of the greenhouse effect. What actually warms our planet is that layer of gases around us that takes in energy, provides quite a degree of warming, 33 degrees in fact. So when we look at that, what we can see is this pertains to the average temperature on the surface of the Earth. Paleoclimatology. This was something that was also mentioned as a topic in this seminar series, getting ideas of what the climate was like in the past through various different proxies. This is quite instrumental in what we actually do with respect to climate models, and we'll get into why that is as the lecture continues. And of course, natural climate variability. And natural climate variability really comes in the effect of the idea of, what is the difference between the climate change that's going on now and the climate change that has really happened in the past as well. So this pertains to long-term climatic changes. And of course, many people know that various different times have had significantly different climates than we have now. Of course, those are in the very distant past. And what's different between that climate change and what's going on now? Now, in particular, what we bring in is the human element to climate change, where we look at what's called anthropogenic climate change. And Dan's talked about this when he was giving the introduction. And really this means that at the present time, climate change is being caused principally by human beings and the actions of human beings, that we are actually having an effect on overloading the atmosphere with what are called radiatively active gases. Now, these are gases that absorb energy and then re-emit it, and that really contributes to an enhanced greenhouse effect. That's alluded to that point that I just mentioned about the radiatively active gases. This is the primary mechanism that actually drives climate change as we speak about it today. So oftentimes you get questions. And if you go on some of these social media pages that look at climate deniers or anything along the lines, they ask questions like, well, climate's changing. What's going on with respect to climate change that happened in the past compared to what it is now? In particular, I think that what's really interesting is being able to educate people on the subtle differences. And it's those subtle differences that are very important in actually being very knowledgeable about this particular topic. So if we look at some of the background with this, and this is kind of a little more on the scientific side of the things that we'll speak about today, what we'll see is that in order to actually represent climate systems, we have to really have an understanding of what systems are. And if we look at that, this is pretty much a set of masses or storages of energy that are linked by storages of them together. This very simplistic term here that connects A to B to C is an example of a system, and this could be all kinds of different things that actually happen in nature. Where it comes in from there, and what the talk is generally focuses about, is that systems operate in nature all the time. They operate in all kinds of different various systems, for lack of a better word. But what we look at is an idea, a representation, and models are a representation. They're a simplified version of reality that essentially comprises the essential elements of a problem, which are expressed in either conceptual, physical, or mathematical terms. And we see I've had provided a nice picture here from the internet that shows us an example of a hydrologic model. So what we're trying to do here is that we understand in reality that this is a system which is governed by several different physical laws. We're trying to understand the links of those physical laws so that we can understand what happens spatially in this system as it continues. Continuing on with that, there are several different types of systems. And the first type of system that we'll look at is called a deterministic system. Now, in a deterministic system, I've simplified these examples for the most part, but we can basically describe a system whose temporal and spatial evolution can be predicted exactly for the most part. And what we mean by that is that we have a very good example. We understand completely that in all cases, A leads to B leads to C. Some scientific ideas fall very easily within that. A good example of this is dominoes. And if we look at dominoes, we can see that these are governed by a deterministic system. We understand the laws that are basically acting on them. Gravity, if you push one over, it will imply a force onto the next one, which will topple the next one, and so forth. And we understand the system from that point forward. The next type is called a stochastic system. And in a stochastic system, what we can see is this is a system whose output is basically governed by a probability distribution. So these are used to cover the idea of randomness or chance. And I always like to bring the example of the Super Bowl coin flip into my lectures when I do them, the idea of this, that coming up with the idea of randomness or chance is governed by a stochastic system. Now, the last type of system, which I still haven't figured out myself, but I will talk about, is that of a chaotic system. And in these are associated with deterministic events, but they are inherently not necessarily predictable in the same way that we think of that. Examples of these include planetary orbits. So why have I gone on this kind of tangent about talking about this? And in particular, when we look back at these systems, what we can see is that what's important is that feedback can develop in these systems. And these are basically a system, a portion of the system that becomes changed and then is either amplified or diminished throughout the system. It can be positive or negative. So what's an example of feedback in a natural system? Well, if you hear about permafrost, which is of course perennially frozen ground, one of the things that you'll hear is the idea that trapped within it is methane. And methane is of course a powerful greenhouse gas. When released, it contributes to global warming in quite a substantial manner. Now, if we are to thaw permafrost, which has methane trapped within it, what we will see is that we will, in a sense, we will be thawing permafrost, and as a result of that, releasing more methane. As a result of that, what we'll see is that that will recontribute to the amount of warming that's actually happening. And this is what we mean by a feedback. It's the same example for the most part as seeing that example of a microphone with that terrible distortion noise that continues. It continues and it amplifies itself through the system itself. Now, another thing that we can see from this is that overall, what we will see is that there is overall warming as methane is released. And this is a positive feedback mechanism. So if we look back at the idea of systems themselves, what we can see is that they include the ones that are predictable. They include the ones that are random, and they include, of course, ones that are chaotic, governed by a deterministic system that is inherently not predictable. Now, if we look at these, well, why have I introduced these concepts? Well, in particular, even though they're a little bit more than I've had enough coffee to really understand completely tonight, what we can see here is that the reason is because weather is actually seen as a chaotic system, whereas climate is viewed as a deterministic system. So when we look at that, well, what does it actually mean for prediction? And if we're looking that weather is a chaotic system, climate is deterministic, well, that goes a long way in actually seeing how we can predict things. One of the big questions for some time has been the idea that what kind of confidence do we have in climatic models when we can't get the weather right 12 days in the future from now? And of course, when we look at the type of systems in which they actually operate, we can see why this is actually happening. So if we look now towards climatic models in general, well, before we get into this, it's a good idea to give a little bit of background as to what actually a climate model is. And if we look at a GCM, or a global circulation model, or general circulation model, or global climate model, which basically all means the same thing, what we can see is that these are very large computer programs. There are attempts to basically simulate climatic processes running through multiple numerical algorithms. They are based on physical laws, and they are numerically generated computer programs. We can see that later generations of these have very, very fine grid cell resolution. And what does that mean? Well, whenever I talk about grid cell resolution, I like to use the examples of high-definition televisions. And in particular, what you can see is that you can think of the old climatic models as being standard definition televisions. Nobody wants to watch those anymore. They have very, very coarse squares, very large squares that make up the image. As time has progressed, well, what the big difference has been increased computer power. And what that's allowed us to do is make more and more fine resolution models of what is actually happening. And in particular, what's interesting about this and why we look at this is it allows us to look at the behavior of these various systems. Now, before we get into the idea of actually looking at how this really comes about, a few words are interesting to really put out there, that of scenario and that of prediction. And if we look at scenario, well, of course, this is a word that I use quite a bit. It's in the title of this presentation. And what we see is that this is a postulated sequence or development of events. And of course, I'm sure everybody's saying, I already knew the definition to scenario, but of course, we're putting it into perspective right now. So also looking into there is the ability to predict. And in particular, one of the things that we want to do whenever we model, whenever we do anything in science, is we really want the ability to be able to predict in these various different systems. Now, one of the good examples that I always like to go towards when I'm actually describing prediction really looks at some of the things that I find very interesting. I also, when I give these presentations, I like to really be able to harness the interests of students. And for that, I focus on the world of NHL hockey. Now, that being said, well, what does this have to do with climatic modeling in general, or modeling of any sort? And what I find interesting about this is that, in particular, a video game produced by EA Sports. Well, every year they produce this video game, and I think they've done it for 20 years or so. And in particular, during the NHL lockout several years ago, some friends of mine got together with me, and we were so hard up for hockey that we actually put the computer against the computer and watched the hockey game. Now, that being said, somebody else had this idea. Yeah, Daz, we almost did it a few years ago too. So needless to say, some people had this idea of doing this. Well, what could we do if we put this together? Let's do this and find out who wins the Stanley Cup. And in fact, they actually do this every year, where they come together and they play the computer against the computer, and they have it compete for the Stanley Cup. They play a whole regular season, and they play a whole playoffs, and you can see that the structure comes down. Of course, Toronto loses in the first round to Boston again, so no big surprises this year. But what we can see is that they've made a prediction here. And EA Sports has predicted that the St. Louis Blues prevail over the Pittsburgh Penguins in, what does it look like, 4-2 to win the Stanley Cup. So one of the things that's coming to your mind right now is it asks the question as to how could this happen, first of all? How could Toronto lose again? But really, in reality, the idea of how we really bring this model together. And what it shows us is that it's a really good example of what we actually look at and do with respect to climatic change modeling, in that multiple factors contribute to things like team success. We looked at the elements, we looked at the influences of climate in these various different areas. We can basically start to get an idea from a modeled perspective as to what would actually happen in any given place. So just like this particular EA Sports example, what we can see here is that there are multiple factors that contribute to an output that we have at the end. So of course, this particular analogy starts with, instead of the elements and the influences of climate, we look at, the stats of hockey players. We look at the chemistry of these various different players together. How do they work together? It also takes into effect various different types of systems that we can look at. The probability of randomness or chance is put into there as well. Other factors, including things like injuries, trades, things that could happen that could affect the output of the hockey season according to this particular analogy. So what we can see about this is that these factors or these variables really come together to affect this output. So one of the things that struck me as interesting, of course, when I saw this and after we watched several games of simulated hockey, well, what we saw is that there were ways to improve this particular prediction. For one thing, they only do this once and they come up with one result. In reality, when we look at general circulation models, we can see that there's actually several different runs that come out, hundreds and thousands of these that actually come out to get a desired result when we look at that at the end. So now that we've kind of given a nice analogy to that everybody can relate to, we really come to the idea of how do we apply this into climatic change, into modeling and actually simulating these elements and these influences on climate in these various different spaces. So coming back to the idea of GCMs, we can now look at them as to what they are. We know that they're very large computer programs that look at very fine resolutions of the Earth to understand what's actually happening with respect to the weather and climatic patterns. Originally, these were put together for a form of weather forecasting. Everybody wants to know what is going on with the weather. Of course, if you could know what was going on with the weather in a week from now, in a month from now, or in 3 months from now, or even a year from now, well, that would be worth something to somebody. And of course, what actually happened in reality was that we found that these systems are not necessarily predictable, that they're governed by chaotic systems rather than deterministic. As a result of that, the intelligence that these have for weather forecasting is about 10 days. And by the end of that 10 days, it is greatly affected by any type of error that might be carried throughout the system. That being said, though, it brings up the fact of what a lot of climate change skeptics like to say. This being the case, how can we simulate what's going to happen in 20 years or 50 years or 100? And of course, again, this comes down to the idea of the differences in systems that we're actually looking at. As an example for this, if you get up every morning and like I do, turn on the weather network, you'll see that there's an average temperature that is assigned for that given day. And any given day, you get an idea whether or not the temperature that we're going to have is above or below that. That average temperature is pretty much put together from an average that is compiled from the last 30 years of temperatures. And of course, it's not necessarily the direct last 30 years, but what we can see is that they operate in what's called climatic normals. So how are these models really constructed? And one of the things that I like to do is operate with these lectures with a question and answer type of standpoint. And for the most part, they are derived from basic physical laws that we can see. Physical laws of things like Newtonian motion. One of the big advancements in climatology was the idea that we could apply Newtonian physics to air parcels that we actually look at. These are what these are based on for the most part. They're subject to physical approximations through mathematics. And of course, a model being a simplified version of reality that essentially tries to encapsulate the essential elements of a problem, well, we can honestly expect it not to get everything. If it got everything, well, this would be basically a model of the Earth itself. And we're just trying to basically encapsulate the essential elements of what's actually happening. That being said, climatic models have not necessarily improved or evolved that much in the last 20 years or so. But in particular, we are getting more and more detailed results. So if we're not seeing that the basic mechanism has really changed in this, well, how are we getting more and more increased results? Well, what I mean by that is that the basic physics behind the model and what drives the air particle, pressure in various different systems, hasn't necessarily changed. But what the big factor is that has changed is the amount and the speed in which we have for computing processing power. That being said, we can continue to make the pixels finer and finer and finer and improve them by including more and more data. But the general steering mechanism to this has basically been very similar for some time. That being said, another question that probably comes to mind is the idea of how do you test these types of things? There is no time machine that we can get into. We can't go to the future and say, oh, my model was right. I said that it was going to be this temperature by the year 2100, and this is what's happening. That being said, it goes into how we actually run these systems. And in particular, they're first run for a current climatic distribution, what we expect things to be like today or sometime in the past. So that being said, this is where the realm of things like paleoclimatology comes in. Because what's happening is that we're spinning up the model, as the terminology is basically called, in order to predict what things were like in the past. That way, if we can get a good prediction of what things were like before, as an example, the Industrial Revolution, or before those various times, well, we can get a very good example as to what it will actually behave like when we change things to input what has happened as a result of human behavior. Now, we put that in as an effective doubling of CO2. So basically what that means is that we take twice as much CO2 as naturally occurs in the atmosphere, and we run the model to look at those results. The differences between these two runs is viewed as the statistical difference in the atmosphere, and that change, or what we see as an increase, is what we can see. As we mentioned, I just alluded this, because we can't see what is in the future, that's essentially the way that we test these models. Oftentimes they come under criticism because people will say, well, that's not testable, you're testing a model with a model. But what we try and do, as we mentioned, is to simulate what climate was like for some known time in the past by starting the model at some other point. One of the biggest problems associated with earth sciences or any type of science in general when you deal with modeling is the idea of where do you come up with initial conditions? And in particular, where do you start from? Do we start at the beginning of the Earth itself, 4.6 billion years ago? Well, that's a very long time ago. Is that really relevant towards what is going on with modeling what's going to happen in 50 years from now? As a result, you have to pick some time that you have data for as well that you can basically spin the model up towards. If we look at these, what we can see here is that the differences, as I mentioned, between the models and the new system is what's really important. And this is why, and this is where it comes in, the ideas is that we can really focus on and actually model the differences between climate and these actual differences that we see in weather patterns. And in particular, what we can see is that where are they most accurate when we look at the results of global climate modeling? And of course, it's at a global scale. That being said, it's the type of thing that you get a very good picture of what's going on, but the picture is generalized. It's not specific. It won't be able to give you exactly how warm your neighborhood in Kingston will warm up with a high probability of success compared to how good the success is for the most part in a generalized area. That way, for the larger areas, we can get a good idea. Areas the size of continents, as an example, or at a global scale when we look at it. That being said, we're kind of coming into the idea of when Daz talked to me about doing this talk, what he really wanted me to speak about, the idea of climate scenarios and how we get these, how we drive these. And of course, these scenarios are quite important with dealing with what we expect to happen. So if we recall, though, the idea, climate change is a human problem. And that's something that I really want to emphasize, in that this is a problem that has been created by humans and that is ultimately a problem of our own. The Earth will still be here after we have the various results of anthropogenic climate change. But how it affects us and what is happening to us is very much a human problem. In particular, another good quote that I'm going to bring up is that was said by Al Gore, who basically said that climate change is a moral issue. This is another one of these type of quotes that resonated with me as it's said at the end of An Inconvenient Truth. And in particular, this also got me thinking, the idea of how this can really be perceived as a moral issue when it comes down to it. This is why the study of climatic change really kind of transcends that of science, that of various other social implications, and really all of geography, biology, and almost everything in between from there. So what we can see is that in order that we know that this is a human problem, it's going to be driven by human behavior. And this is hence where I got the title for the presentation here. This being said, it makes sense because we don't know how the story is going to end for us to take a scenario-based approach to this. And this pretty much means that, it has multiple endings. It's kind of the same thing that you looked at when you probably looked at your life. Your first reaction was that you were going to be an astronaut cowboy. And when that didn't happen, you probably came up with other scenarios. And when that didn't happen, well, you decided to study climatic change, like I did. But for the most part, what we look at is a variety of different things. And projections are some of those. So projections into climatic change really heavily depend on future human activity. If this is a human problem which is being driven by human events, well then obviously how we act going forward is going to have a very large impact in what is actually happening with respect to the amount of climatic change that we can expect. That being said, the people who kind of run this, the Intergovernmental Panel on Climate Change, the IPCC, has several different scenarios, and these are put forward by the work of countless individuals. And everybody really plays a part in this, everybody who's published within these domains, whatever it might be in permafrost, ecology, various different areas. This goes a long way in actually explaining what these scenarios are going to come up with. As we mentioned, there's about 40 of these different ones that look at different assumptions based on concentrations of greenhouse gases. That's pretty much what's driving it, but in particular, what's driving the concentrations of greenhouse gases. And if we look at this, this is a nice little figure that has been put together by the IPCC that looks at 4 of the most popular scenarios. When it comes down to it, I mentioned there are 40 of them, 10 times what is actually here. But in reality, what we can see is that they are basically cousins of these particular ones. We can see that what is actually important from this diagram has to do with the sustainability of human development, as well as global cooperation as well. We see that these influence factors like population, remember that 7 billion number that we talked about before, well, it's very easy to have a big impact on a lot of those people in general when you have a population that is that large in a diverse world like we have today. Also things like the economy, technology, various other things, energy, agriculture, land use. These are all things that really stem into what is going to go on with respect to climate and how it's going to change. And of course, they feed into the various different scenarios. Another graph here, this nice one by the IPCC again, shows us what happens as a result of these different scenarios. We can see there are several different lines on here pertaining to these various different scenarios, things like A1FI, A1B, and of course we haven't really explained what those are yet, but what we can see is that there are quite a bit of differences that are put in here. We can see that those are represented by the colored lines. Of course, the higher it goes, the more warming is essentially what this graph is telling us, but you also might notice the shaded gray areas in there. And this kind of brings up what I was mentioning about the EA Sports forecast. When I mentioned that they only did one run. They only did one run to see who was going to win the Stanley Cup. And in reality, when you model, you do several runs. And these several runs basically are encapsulated by the end members on this particular gray shading, where we can see that that's the outside of that, and the lowest possible and the upper possible. These are what we got from running the model normally. And the lines that are actually there are what's on there from representing it several times. If we look at some of these particular scenarios, we'll start with the first one, which is termed A1 for originality for the most part. And when we look at this, we can see that the A1 scenario is operated in a more integrated world. This world is for the most part characterized by rapid economic growth. So this sounds very good for some people. If you're an economist or somebody who has stocks, this is of course exactly what you want to hear. What we can see here is how does this really trade into things like population? Well, if we look at this, we can see that global population reaches approximately 9 billion by the year 2050. That's really not that far away when you actually think about it, and then gradually declines from there. In particular, the fact that we are peaking in population and declining from there is really a very big steering mechanism to what is actually happening with respect to the climate models. From there, there's also a quick and efficient spread of new technologies. New technologies are quite important, whatever they might be. And in particular, a lot of things drive new technologies, and we'll look at these in some of the subsequent other lectures that are presented in this seminar series. In particular as well, what we see is it's a convergent world, in which case we have income and way of life that is really convergent between the different areas that we look at. And we have extensive social and cultural innovations worldwide that we can, or interactions worldwide rather, that we see. So there are also subsets of these models. As I mentioned, we'll focus on 4 of them because those are the 4 that are generally used the most. I use these when I look at things like the amount of permafrost decay that we would expect to see that will be simulated by these. This is how they work in the various different scenarios. We can see that there are several of them in this A1 family, which is quite an aggressive path of social behavior. We can see that we have things like the A1FI, which is a more fossil fuel intensive type of scenario when we look at it. A1B, which is a very popular one. It's a bit of an intermediary that we see, which focuses on a balanced life between balanced energy sources as well. Now, of course, this could be the difference between bringing things in like hybrid cars and staying with conventional types of engines as well, that we can see the difference between these different things. Also, we have ones that focus on, such as A1T, that focuses on enhancements, on emphasis on non-fossil fuel energy sources. And I'm not an expert on energy sources by any sense, but I can see how this is basically driving this. If overnight we come up with something that's much more profitable than fossil fuels, behavior will change. But in general, a lot of things don't change, and they only make sense in the light of catastrophe or something that could seemingly happen that is bad. That's what really progresses how technology changes and what's driving the scenarios. The A2 scenario, on the other hand, shows a much more divided world. This is really predicting how human evolution, cultural evolution will continue and how that stems on from climatic change. The A2 family of scenarios is basically characterized by seeing a world that is more independently operated with self-reliant nations, less collective community work that's actually going on, continuously increasing population. Important in the A1 model was the idea that population peaked at approximately 2050 at 9 billion. This sees continually increasing population. With that, that puts increased pressure on things like food issues, on agriculture, on water, sustainability, these types of things as well. And we can also see that this is a more regionally oriented economic sense of development and what's actually happening. The next series that we look at, and of course we do focus on kind of the aggressive and the end members that we see in these, covering a wide spectrum, is that of the B family. And in the B family, what we can see is that the B1 scenario is a more integrated world, more ecologically friendly, and it's characterized by rapid economic growth, as in A1, but with rapid changes towards service and information-based economies. So we can see where this would generally steer us towards different types of behavior, different types of carbon emissions that would come out as a result of this. Population is rising to approximately 9 billion again by the year 2150, and then declines again as it would in A1. You can see if you look back at the graph, though, that there are significant differences with these two different scenarios with respect to the amount of warming expected, even though they have similar population trends. It all comes back to the changes that are being made within them. We can also see that there are reductions in the intensities and the introductions of more clean technologies that are used in this particular scenario, with emphasis more on global solutions and social and environmental sustainability. The last scenario that we'll kind of look at, and as I really must focus on, there are several of these and different cousins and offshoots of these. Well, what we can see here is that the B2 is the last one, and this really shows a more divided world, but more ecologically friendly for the most part, which is characterized by continually increasing population, such as what we see in A2, but rather here we have more of an emphasis on local rather than global solutions for things like measures in the economy and, of course, environmental sustainability. We also have intermediate levels of economic development. So we're not seeing that rapid economic development that we expected in some of the other scenarios. These all play a very big role on carbon emissions that we look at. So what we can mostly see from the B2 scenario is that there is less rapid but more fragmented technological growth in A1 as in B2. So it really comes down to the idea, now that we presented some of what's behind these models themselves, we look at the idea of, so which is it really going to be? And this is a real question because it really focuses on the fact that these are seemingly quite arbitrary when it comes down to it. Which one is actually going to happen as a result? Well, one of the questions that's in there is, if you read through the IPCC report itself, there is a section that says frequently asked questions. And in those frequently asked questions, I often say that if you read through those and understand what's on there, you'll know more about climate change than almost everybody out there. And it's very true. And they ask questions like, how reliable are the models that we use to project future climate? And of course, this depends on a lot of different things. We know the differences. We know the differences between weather prediction and climate prediction. So global climate models have evolved significantly. As I mentioned, what is meant by evolution? Well, it means that our pixel resolution is getting finer and finer, but also our interaction between different systems is getting much more complicated. The idea that the ocean interacts with the atmosphere, the idea that the cryosphere interacts with the atmosphere. These are all linkages that are being put together in these models themselves. So the models will also and should always be viewed critically. And when you say critically, you mean that you should take them with a certain degree of a grain of salt, but not to insult them and not to say, well, they haven't done their research, that this is not right. A lot of time and effort goes into all these, from the scenario-based approach to the actual physics and the modeling of it itself. But remember what's important, how we test models. And in particular, what's really interesting about the model itself and what we should really look at is not necessarily the absolute numbers. People like to stop and say, well, you said that it was going to be 21 degrees today and it's only 20.7. Well, that's not really what we want to focus on. We want to focus on effectively modeling the behavior. That way, when we perturb or change things, we can look at that difference that we actually see. And that difference is what's actually important rather than the absolute values. If we look at the uncertainty of these models, well, what we can see is that these pretty much show that on a global sense, when we change the scale, what we have is that the scale, as it increases with respect to spatial area, we can see that we have high confidence that warming is actually occurring. As we increase that towards more local environments, we have less confidence in it because it's easier to predict generalities. The same thing happens with respect to precipitation, to soil moisture, and of course, ice and snow increase and decrease. Predicting things for specific areas is quite a bit more difficult than predicting them for larger areas as a whole. With respect to things like mean temperature, so what happened if we all stopped it overnight? That's another question that gets asked quite often with respect to these. Well, what would happen? Would climate still continue to warm? And of course, like a lot of systems, what actually happens is that climate has significant momentum and memory to it. And what it means is that this is the equivalent of actually driving a car at 100 kilometers an hour and then running out of gas. You're not going to completely stop right dead in your tracks because so many other things are driving that system. And it's very similar. A new equilibrium has to be established. So a lot of what's actually happening today, preventative measures, well, they'll continue, and warming will continue because that warming is seemingly still in the pipeline. It doesn't mean that we shouldn't do these types of things because that will help things as they continue. But the question really comes up is that, does the capacity for this exist? And you really see this when you take a show of hands and you ask people, well, how many people would expect a halving of their quality of life? And it's very difficult to go back on these. And really what you want to do is set these systems up so that they can be sustainable going forward. If you look at other elements in there with respect to predictions of climate change, we also see that extreme events become important. That, remember our original definition of climatic change, that these are average changes or also changes in the extremes that we see. So what does this mean in particular when we see this? Well, extremes include things like droughts and, of course, more intense storms. We can often see that things have changed. We see hurricanes in New York City much more frequently. We hear about that quite a bit because these are areas that don't typically have those types of storms. They're not built to withstand these types of storms because historically there haven't been that many of them in these areas. Other extremes. Have you seen an extreme lately? 2 years ago, in March, almost around this time of year, it was 20 degrees Celsius in Kingston. And that is an example of an extreme. It had not been that temperature at that time of year at this place for thousands of years. And that's a really specific example of extremes. In particular, just before I end, I'll kind of draw some attention to sea level rise. And projections of sea level rise become quite important because what we see is different numbers under different scenarios. Everything that we can see from the various different scenarios predicting various levels of sea level rise. In particular, I think that what becomes interesting when you hear about sea level rise is you hear things like Manhattan being below these particular limits, and that Manhattan would be flooded under these scenarios. Now, one of the things that I've seen with respect to, places like Manhattan is that they're not going to just let that place get inundated by the sea. They will take every measure, basically, and spend an enormous amount of money to prevent that from actually happening. In particular, where places are very vulnerable is places that don't have the luxury to do that. Places that are below sea level, where millions of people actually live, like in Southeast Asia and India. And in particular, I think that sea level rise is one of the biggest problems associated with climatic change. Because what happens is that you aim to displace people. And you can think of living in your house, and then all of a sudden, if you had 10 other people coming to live with you, well, what would happen? Well, people are people, and things would boil over. It would become a problem. And it's very similar. What happens when you displace all kinds of different people from all over the world? Where are they going to go? And that's really what really brings up and why these predictions of climatic change are actually quite important. I actually see that sea level rise is particularly one of the most difficult problems associated with climatic change. And the reason for this is because, as I've mentioned, climatic change is a human problem. And what happens is when we have human problems caused by displacement, things like disease, war, and famine break out. And these are the types of things that we're really trying to avoid. So when it comes down to predictions, we also can look at some of these ideas with respect to what is actually happening. And we look at that close to home with respect to Canada. And if we look at typical examples that we would see, well, we see amounts of warming, 2 to 4 degrees in the summertime, 6 to 10 degrees in the wintertime. And in particular, what we see is that climate warming is an asymmetrical phenomena, where we tend to see much more warming in the wintertime compared to in the summertime. Remember, though, Canada is a very large country, and what do these numbers actually mean when it comes down to it in particular? Well, in a place like Canada, what it means is that we have a northern amplification of climate change. A lot of this is due to feedback covers, and what we can see is that this means a reduction in snow cover, which has all kinds of hydrologic changes associated with it, but it also means that we have energy balance changes associated with this. The darker something is, the more energy it absorbs. This feeds back into the idea of feedback mechanisms that we looked at in particular. So if we look at a response to this system in particular, what we can see is that it's easy to stand up here and give numbers. I could say, 6 degrees, 5 degrees, 10 degrees. But what does it really all mean when we put it in perspective? And when we look at it this way, what we can see is that to date, climatic systems have warmed at a global amount by about 3/4 of a degree Celsius. And we've seen significant impacts as a result of this. Impacts to plants and animals, impact to farming, impact to service industries like the ski industry as an example. This is not the best winter to use that example, but remember 20 degrees in March. So when we use these examples, what we could see is that more warming is predicted, and it's predicted under these scenarios. And what we can see is that if we ever are to achieve the upper limit that we look at, about 6.4 degrees globally by 2100. And in particular, one of the things that also resonates with me that I'll say is that I attended a climate change lecture once, and it was given by a woman who was, in her 70s. And she mentioned that one of the things that puts climate change into perspective was having a grandchild. And the reason she said that was because it was a form of reach, and she basically had a reason, some part of herself that would be here to see this. And in particular, by the year 2100, that's really within a lifetime. I have a 2.5-year-old daughter, and I hope that's within her lifetime that she would see some of these problems associated with this. And in particular, if we reach those upper limits that we see, well, that actually represents 10 times the amount of climatic warming that we have seen to this particular point. So that's something that really puts the numbers into perspective. At the biggest point, what we can see that is driving these systems is that we have uncertainty in our systems. And a lot of the uncertainty is really governed by what we call subsurface grid or subgrid cell level problems. Things like cloud cover, things that operate at a smaller level that can be represented in the computer program itself. As a result of that, we see that these represent the biggest challenge in modeling today. And as computer systems evolve, as things like remote sensing, which plays an increased role, satellite coverage, and actually seeing what's going on increases, well, this will help us. The world is really, when it comes down to it, infinitely complex. So as a result of that, what we really have to do is find a way to really constrain this by understanding the essential elements of the problem itself. So in essence, we really control the scenario. We are what's going to happen as a result of this, and now we've seen what goes into these various different scenarios. And I'll just end it at that. Thank you very much.